Well, great. So most of the other speakers have been talking about the future, all the new products that Nokia is shipping. I want to change gears a little bit because as we talk about the future, it's also important to understand the past and how we got here. So I began my career some 25 years ago working in one of the first network operations center, working on network management, network automation, and network security. And to provide perspective of what that looked like in 1993. In 1993, this is the Ann Arbor NSFNet Network Operations Center. In collaboration with MCI, IBM, and the University of Michigan Merit, we built the first T1 national backbone. And two historical asides while I'm here. Number one, only one person in the picture actually worked for us. We learned the New York Times was coming that afternoon to do a photo op. So we quickly gathered other folks from the office to come in and look like they were backbone engineers. The second, and this, by the way, I am very proud of, I had recently seen the movie War Games. And I thought that all network operation centers should have glowing red lights in the background. So that was my contribution as well. Back in 1993, network management was really an afterthought. We were so focused on building the hardware, on the speeds and feeds. You know, network management for us meant 5-minute polling. We would do monthly updates to the router config and do traffic engineering once a month. And, you know, for the most part, network management was an afterthought. And I know this for a fact. The reason I know this for a fact is because they assigned it to me. The newest person right out of school, that was my role initially, working on the network management. And it drives me crazy when people say back in the early days of the internet, we never thought about security. We thought about security all the time. We just never did anything about it. It was always something that we sure would get addressed down the road. So back in 1993, we had SNMP polling. We had black and white gray screens listing maybe 10 or 12 SNMP traps per day. And that was largely the way we ran the backbone. Of course, over the last 25 years, the network has changed. We went from web-based applications to video to now the pinnacle of applications and my son's favorite game, Fortnite. All of this, of course, changing the demands on the network. Changing it from how do we do high-speed video, how do we do low latency, high-performance gaming. And while a lot of focus has been on the applications, I don't think there's been nearly as much press or recognition of how much the underlying backbone has changed. Back when I started my career, ISPs largely controlled their own fate. The backbone engineering they did had direct impact on performance. They could do planning and nice curves over the traffic growth over time. Back in even 2005, folks like Akamai were tiny. Akamai was just 30% of the network. But as you look at this graph, we're graphing for North America over the last 15 years or so, how much CDN, like Akamai, Netflix Open Connect, Google GGC, contribute at peak as a portion of the network. We've gone from CDNs being an adjunct to the network, a nice to have, something that helps offload transit, to by the time you get to this month, in 2018, this is the network. It's 90% of traffic at peak, on average, across North American providers. And this, by the way, is traffic that is not under the control of the operators. This is traffic that has real-time adaptive bitrate, Google moving traffic around, Netflix moving traffic around. Huge traffic demands moving, not on a daily, not on a monthly basis, but often on a minute-to-minute or a second-to-second basis. But while carriers no longer control the vast majority of traffic, they certainly get blamed. when there are not just outages, but when there are slowdowns, when there are videos slow to load, it's the carriers that get blamed on Twitter or terse emails or Instagram or wherever. And for carriers are facing a really complex network filled with third parties like CDN, with EC2 and Amazon, some devices in their network with Akamai caches, others direct peering, huge volumes of traffic moving out of national data center peering into regional, into metro. Just massive changes in the network, massive changes in the time scale, all having direct impact on money. And it's not just the traffic engineering that has changed. DDoS used to be an annoyance. It grew and grew, and my previous company actually did DDoS for 15 years. And I think around 2011, we thought we had DDoS mostly licked. DDoS had kind of disappeared from the public conscience. It went basically a year between New York Times articles about a DDoS outage. 2011, massive amounts of third-party hardware had been deployed everywhere in the network. And I think we'd done a pretty good job by 2011 in blocking the DDoS attacks. Of course, the world changed. And I'll talk about why in a couple slides, but clearly we've seen massive new threats emerge in the internet. We've seen New York Times and the Wall Street Journal, the Financial Times, again, have headlines about attacks impacting large customers in large portions of the country. I lost Spotify for a period of a day due to one of these attacks, so I felt it personally impacted me as well. So with all these changes in the network, massive changes in the hardware, we've seen advances today and throughout the earlier plenary about just these great advances in hardware and technology. We've seen massive changes in the applications and the traffic. The big question is, has how we run the network changed? And in particular, just a quiz for the audience. We'll make this participatory. Is this a screen grab from the NSFNet 1993 NOC, or is it a NOC from today? How many think it's a recent image? Okay, a few hands. It turns out it's a couple years old, but it's not far from the mark. Typically, a lot of providers continue to manage with massive S&P polling, event-based management. Of course, the big difference is back in 1993, we had 12 alerts per day. Now I visited carriers that have 20,000. And by the way, a quick story. I was always fascinated. How do you handle 20,000 alerts? So I spent a day embedded in a NOC. And I learned when I started the shift with the NOC staff. We came in, we had our coffee, our donuts, and when they got on shift, the first thing they did was delete all the alerts. Theory being, if it was important, they'd come back. So that is network management for a Tier 1 carrier in 2018. I was right at home. It was what we did some 25 years ago. And it's not just again the alerts, but the security landscape has changed. Basil touched on it a little bit. One of the really big differences is the number of IP devices out there. So quick fun exercise. By the way, anyone can do this. It's cheap. You can spin up some 50 Amazon crawlers, give them 10 minutes, give them the ASN and IP CIDRs of all the North American providers, wait 10 minutes and see how many accessible IPs you find. And there's hundreds of thousands of these internet-exposed post-NAT web cameras. Hikvision was the one involved in the Dyn DNS attack. But there are hundreds of thousands, millions, in some cases tens of millions of these devices out there. And oh, by the way, that number is growing. All these devices we're seeing now participate in different types of malware and denial of service attacks. Though it's not all bad news. I will say that some things have improved in security. Back in 2003, we had a stupid SMB Microsoft vulnerability, Sapphire, Slammer. Took 6 weeks. huge portion of the internet compromised over the course of 6 weeks. After billions of dollars of security investment, upgrades, hundreds of thousands of hours of effort, by the time we get to 2017, the efforts are clear. We go from 6 weeks to infect most of the world to 6 hours. Again, I'm being somewhat facetious, not much progress at all. In fact, just the opposite. And, as we look at how folks manage the networks, how they do security, security continues to be an afterthought. It's something you buy third-party devices for. It's something after the fact you add ACLs. I was watching a video, how to block DDoS recently, a tutorial on the internet, and it really hasn't changed in the last 20 years. The advice is add ACLs, add hardware like specialized devices to your network, or disconnect the customer, which is by far, continues to be the most common way to address DDoS, is to find the victim of the attack and disconnect them from the internet so that the attack no longer harms your infrastructure, though of course it doesn't really help the customer under attack. So I think when we started Deepfield, now some 5 years ago, it was clear that we needed to play the game, and I'm continuing my war games theme here. We needed to play a different type of game, or play the game in a different way. Our goals were really betting on that the hardware would get better. When I started my career, getting any data from a router was really hard. Installing ACLs on a router was really hard, or you were concerned about crashing the router. So we really hoped that hardware would get better. It had to get better. We had to change the conversation from 100,000 links and elements to what is happening in the network, what is the quality? Because it's really hard to look at an IP address or a link and know much about what is happening in the network. So we needed to raise the bar on the conversation in the way we manage networks, to understand not IPs, but applications, not just IPs, but the subscribers, and really provide a key component of the tech for what we thought would be the emergence of new, smarter networks, where security, traffic engineering, traffic management, automation were not an afterthought, but were built directly into the network. So our goal with Deepfield was, number one, support all routers. Absolutely support Cisco, Juniper, collect data from them using IETF standards. But where it's available, and this was what got us really excited when we joined Nokia, but where it's available, if you have a vendor that has gone the extra step, that has built the FP4, where not only does the FP4 have terabit or multi-terabit forwarding, but has native policy, has native telemetry, can give us raw packets as well as all sorts of different types of streaming telemetry. Can we take advantage of that? And again, it is just not about just the forwarding. It's not just about the CapEx of the network, but it's about the availability and the operational expense of maintaining that network and keeping it running. And so I'll talk through the rest of these few slides a little bit about how we're not only leveraging data from other vendors, but with the added features in FP4 and Nokia platform, taking advantage of some of those new capabilities as well. So Deepfield number one is software. I used to say we are a software-only company before the Nokia, we joined Nokia. Now, of course, we're part of a hardware company. But Deepfield by ourselves is really software-focused. It's software that runs on Linux servers, 3 or more Linux servers in your network, collecting data from IETF standards like NetFlow and SFlow and BGP and AAA from your network. With this data that we have coming from the network, we first analyze the data. We take in streaming data. As I said, it includes things like NetFlow, basically packet headers, AAA data, DNS data, and we can collect data from global networks at scale with no additional CPU or other hit on the network. All capabilities built directly into the ASIC, that allows us real-time visibility into the type of traffic, where the traffic is going, and the quality of that traffic through the router. We then apply different types of processing and AI to it to understand the topology, to learn the application. In the case of things like denial of service, to understand what does normal traffic look like. And the last thing is if you can do the first two, if you can collect data from terabit networks at scale, as well as, we do 10 gig networks, we do the whole range. But if you can collect data from the largest networks in the world to the smallest networks and process all of this data in real time, if you can build models of normal traffic and process the data to understand not just interface by interface, but to understand application and quality, then you can do the third thing, which is when something changes, either alert or automate. And today, indeed, we both alert and will do things like automatically work with both partners in the FP4 to automatically block and mitigate denial of service attacks. And as I said a few minutes ago, some of our, I think, vision and view is the discussion needs to change. I started my career programming low-level code, assembly. And it's just really hard to scale when you're at that level of doing management. So across the industry, we've seen a push towards model-based netconfig. And indeed, with network management, with automation, with denial of service, we're trying to make the same push. To change the discussion, not just about octets on an interface, but can we talk about higher level business and topological constructs like POP, service groups, CDN? Can we map this data in real time to different SLAs? Understand the differences between on-net and off-net services? Really change the discussion and change the level at which we manage and run these networks. And indeed you can. I'll show a few screenshots to finish off the presentation of some of the things we do with all this data and some of the value that that data provides to operators. So this is actually a European provider without any additional DPI, without any probes in the network, leveraging data from their Nokia routers, leveraging data already available in the network. We know not just the volume of traffic, but we actually know the applications. And by the way, I apologize, I should have scrubbed. Some of these are probably not appropriate applications. But real-time visibility into what's going across the network, what is the quality of that traffic, and where is that going, all without any additional probes in the network. And it's not just about understanding how much Netflix, how much Hulu you have in the network, but it is understanding how is that traffic being delivered. So Deepfield also classifies both the application, but will also understand which CDN is providing it, which hosting, which parts of EC2 or Amazon. And what you're seeing, seeing here, for example, is just a quick map showing Pinterest. It's showing Pinterest being mapped to, some of it's using Facebook API. A lot of that's going through Akamai, and it knows which Akamai data centers, in addition to which on-net caches are providing that traffic. The reason all of this information is useful is that when there's a change in Netflix traffic performance, when there's a sudden shift in where the traffic is coming from, having all of this data is really useful to provide the operator both a view of what changed. Did the video quality change because of an attack, because of a failure, because of something one of the CDN providers did? It's really important to have all this visibility in real time, and certainly the ability to alert on it so remediation steps can take place. So I'll provide one example of where I think all this really becomes valuable. We had one customer in North America that was upgrading their network. They'd spent 18 months spending millions of dollars and upgrading routers and line cards and access network. They were doing everything right. They were doing best of breed practice, updating their network. And initially, their network started where they were in the top 3 or 4 in the Netflix rankings. They then became number 5, number 8, number 10, and continued to fall. They had probes in the network, they were running performance, they were doing all sorts of debugging, but they could not understand why they continued to fall in the rankings. And it wasn't just the Netflix rankings. Some of the comments on Twitter were becoming quite cruel about the performance. It was slowly becoming a board-level issue of what's happening in the network and why is this investment not paying off. And the real problem is they had lots of little it was lots of little data from this section of the network, from this. But they really had no global view of what was happening in the network, where the traffic was coming from, or what the quality degradation, where it was occurring. So we worked with them, we deployed Deepfield. Deepfield was able to collect data from not just one router, but all routers. It was able to classify all applications. It was able to understand the quality of those applications at the POP level, peer level, all throughout the network. And the change was pretty dramatic. Once they had visibility, once they understood, once they could see the network, once they could change the management discussion from what's happening on an interface to what's the end-to-end quality across the network, they were able to effect changes and, basically over the course of a month, went from, way down there to up there. And, oh, by the way, continued to climb in the rankings and the performance impact. So really, really powerful data when you have it, when you can manage your network using at higher levels. And the visibility is not just for Netflix overall, but as I said, it's the ability to look at a particular CMTS and understand, is this CMTS, is this DSLAM performing differently from the rest of my network? How many customers do I have on this DSLAM watching Netflix? What is the QoE? What is the bit rate of the Netflix they're getting? And in some cases, it's not a hard failure. This was actually a soft failure. But to instantly detect when not all traffic, but just Netflix traffic changes quality, or in this case, vanishes from a particular CMTS. And oh, by the way, we know 800 streams were using it at the time of the failure. So it's also about evaluating the impact of that failure. And this is just another quick screenshot showing some of the tools within Deepfield. Again, leveraging data already in your network. No additional probes, leveraging flow, SNMP, DNS. We're able to track the number of Netflix streams and the quality of the streams. In this graph, by the way, is kind of what you want to see. In many networks, you'll see when the number of subscribers, which is the green line, goes up, the quality of the streams goes down. So this is actually a good graph where the average bit rate remains mostly flat throughout the course of the day, while the number of subscribers goes up during prime time. And for various reasons I won't get into, but it's device effect, you'll see dips in the early morning as folks change devices over which they watch Netflix. So really valuable data to have. The first step is, can you collect the data? Can you analyze it? In what I think Nokia, both NSP as well as Deepfield, are spending a lot of time doing now are trying to automate this process. Can we understand what Netflix looks like for your overall network, for a given market, for a given peer? And can, in real time, we alert you when that changes, when there's a quality shift? So you learn about it before your customers are calling. You learn about the DDoS before there's an outage. You can shift traffic to improve quality when Google makes a mistake. All really important data, all very different from the type of engineering I used to do back in 1993. And this is just an example of showing one of those alerts. In this case, we're monitoring Netflix traffic for part of the network. It can automatically identify not when a given interface goes up or down, but when Netflix traffic changes quality or volume or number of subscribers beyond normal behavior in a part of the network. Again, it's changing the game from how we've spent the last 25 years doing network engineering to try to provide larger tools. So as I wrap up the talk, I think the main point is we started network management where it was an afterthought. It wasn't important. They assigned it to me. But as Basil mentioned and others in the plenary, the availability of the network is 100 times, 1,000 times more important than it was in 1993. Security, traffic engineering can't be an afterthought. Security has to be something that is embedded into the network directly. And I'll finish off just talking about some of what we're doing with the FP4. As I said earlier, typically folks would block DDoS attacks by doing ACLs, by spending tons of money and deploying third-party hardware at 40 gig, 100 gig, separate devices all throughout the network. Typically, this would be on the peering edge, but as I think I'd mentioned earlier, we're seeing huge volumes of traffic now coming out of the IoT and the subscriber edge. So one of our goals is, instead of something you add to the network, can we have security, DDoS protection be something built into the network that ships with every FP4, that's part of the card, part of the forwarding plane, that not only can forward packets at line rate, but that can do payload byte offset filtering and blocking and DDoS prevention at line rate as well. So we're really excited about the technology as it rolls out and the products. We are working with customers today, basically not just on the peering edge to block DDoS, but the entire edge of their network, to be able to prevent outbound DDoS from their customers, from their wholesale customers, and from, of course, the internet peering edge, where we've traditionally seen DDoS. We're trying to change the discussion from where large ISPs used to sell DDoS service for 50 customers, 100 of their banking customers, to how do you offer service to every customer, not just ones that you've set up the tunnels for and you're going to off-ramp through, but every customer as part of the effort. And so what we've been building with the FP4 technology as part of Nokia is not just the ability to install ACLs, but can you build a system where you can get real-time payload data about the denial of service attack from the FP4? Can you collect that data, analyze it, compare it to baselines? Can you signal back to the FP4 then to apply policy or to ask more specific questions and install additional ACLs and continue this loop of where the FP4 becomes both a very powerful policy security enforcement point as well as an equally powerful data source as you're correlating data from all around the network, understanding security events in real time. And it's really cool, right? This is something I've wanted since 1993. You know, ever since 1993, and I had my first enabled password, I've found myself logging into routers, trying to understand what was happening with weird traffic. What we have now with the FP4 coming out is the ability to basically ask any FP4 for a given sort of PCAP, TCP dump-like statement to get real-time traffic that's matching that across the network. So really, really powerful capabilities. It's taken 25 years, but we're here. But really excited to have these as a really powerful tool as part of our security traffic management arsenal. So I've spent, I think, the last 30 minutes or so talking both about where we're coming from, where we're going. I referenced, again, one of my favorite movies. This, I think, is continuing the theme, is the Whomper from the movie as well. But the things we're discussing today aren't science fiction. What we're really excited about is it took us a long time. We're here. But the technology we have is available. It's available at least in demos you'll see in the room next door. We are showing off some of the integration with the FP4. We're showing off some of the video quality, some of the subscriber management technology. And we'll also have demos that we're doing as well with NSP and some of the automation. So I appreciate the time today. Hope I see you in the room next door, and thank you very much.